Good morning, everyone, and welcome to the Big Data to Knowledge, a guide to the fundamentals of data science. I'm Jack Van Horn from the University of Southern California, based here at the BD2K Training Coordinating Center, and I'd like to welcome all of you to our second volume, if you will, in our series of data science seminars focused on the fundamentals of data science. We are very excited to be beginning this season with a lecture by Jonathan Entwistle from IBM, talking about collaborative and scalable open source data science. And just a few words about Jonathan. Jonathan has worked in the federal government data science community for over a decade, working with large programs within the NIH, within the Food and Drug Administration, as well as CMS. And he holds a master's degree in Predictive Analytics from Northwestern University. He specializes in data science at scale, leveraging technologies such as Hadoop and Spark. He lives in Maryland with his family, and so I understand he routinely discusses data science at dinner with his statistician wife and his 2-year-old son. So it's good that he's helping the next generation of young scientists in data science. So without further delay, I'd like to invite Jonathan to give his presentation and invite you to send in any questions that you have via the little chat feature that you can see in the GoTo webinar panel. I will go and try to select various questions to ask Jonathan at the end, and I'm sure Jonathan will pass on his contact information and be available for questions and comments offline at any time that you want to reach out to him. Again, just one final thing is that this year we're going to be having a series of these lectures. We're going to be trying to do them regularly on Fridays at this time. We're going to try and steer around the holidays, and so you may find, at least initially, where things are interrupted by holidays. We understand those are important family times and times when you'll all be away. But then certainly things will pick up steam, and then we'll also ask you if you have any ideas for speakers for our seminar series to please reach out to us and make those suggestions. We'd love to have them. Without further delay, let me have Jonathan take it over. We're excited to hear from you, Jonathan. Thank you.
Good afternoon to everyone on the East Coast, and good morning to those of you joining me from the West Coast. Again, my name is Jonathan Entwistle, and you saw my contact information up there. I actually do primarily work with the U.S. federal government, including all of HHS, but I've got a lot of experience spanning all kinds of different spectrums, so if there's folks on who want to talk about cybersecurity or other things like that, I'm happy to do so. The agenda for this presentation is really going to focus on a healthcare use case with some real data. And you'll be able to follow along with me if you're so inclined by going to datascience.ibm.com, and you'll be invited to join what's called the Data Science Experience. I highly recommend doing so you can move along interactively with me if you want, although obviously you don't have to. So for those of you on the phone who are already seasoned data scientists, I have to walk a fine line. You might find a little bit of the stuff at the beginning a little rudimentary, but for those of you who are not data scientists, I think this is going to be a good use of your time. It should be very easy to understand what we're trying to do. I'll try to explain how things work. I won't go into too much detail on specifics of code or anything like that, but as pointed out before, you can always feel free to reach out to me after the fact. So without further ado, I think we'll move forward. Now, one of the major things that data science tries to do is automate the processes that we do every day. And so one of the things that I'd like to do is try to help us predict breast cancer. So I've got my data science console up here, and you guys should be able to see that. And what I'm going to do is head over to the community, and I'm going to look up the data set. And that data set is a breast cancer data set that comes from the University of California, Irvine. Let's just put it in here, and I'll let you take a quick look at it. What you'll see is that in this data set, you've got a patient identifier, you've got a diagnosis of either benign or malignant tumors, and then we've taken structured data that we've gathered from the X-ray. Now, some of you might be thinking, well, you know, data science on highly structured data is easy. teach a computer how to recognize it from a picture of an X-ray, and that's what I'll be talking about in the second portion of this, deep learning and convolutional networks, those types of things. But to set a baseline, what I really wanted to do is see if I could teach a computer to recognize breast cancer, the same way a doctor would by looking at an X-ray. So you can see we've got about 32 columns. We've got a few hundred examples. And these columns, other than the diagnosis, are details that we've taken from the X-ray. For example, if we see a malignant tumor, what's the texture of that tumor? What's the perimeter around it? How much area does it take up? So highly structured data so far. So what I'm going to do is I'm going to create a project for this. I've called it NIH Video. Now, we are talking about scalable data science. So everything I'm doing here, you'll note, is written in either Python or R, and I create notebooks. Now, if you're not familiar with notebooks, IBM thinks that they are going to be absolutely the sort of standard for how we share analytics and code. And what's interesting about a notebook is you can see here, a notebook looks a lot like a Word document. This particular notebook is a Jupyter notebook, which again supports Python, R, Spark, Scala, those types of languages. And what's interesting about them is that you actually can write code and execute code and pull data from these. So we'll be working in a notebook environment today. I won't make it pretty for the sake of us actually getting through the data science part of it. But if you are interested in taking a look at what a professionally authored notebook with professional data is, you could go take a look for, again, classifying tumors with machine learning. So one thing I want to do is exploratory data analysis. So what I've done is I've downloaded that data set that I pointed out earlier, breast cancer Wisconsin data set. So you can do your exploratory data analysis wherever you want, but I'm going to just do it within the data science experience here. I can also show you how you might do it with things like pixie dust in Python. But I want to generate some basic metrics about things. So first of all, we can see here that out of our cases, 357 were benign and 212 were malignant, which means that we've got a slight imbalance of data there. That's probably something we'll need to take into account. And as we look across the others, we don't see any kind of a normal distribution. We just see data, which is kind of data. So if we're trying to predict benign or malignant, you've got a couple of different options. You could go with an example would be a logistic regression, which is really good at deciding between two binary things. But because of our data and how it can be sort of non-linear, non-parametric, we're going to go with a tree-based approach. And I'll get into what that means later. If we needed to visualize something, we could do that here. But what I'm going to do is create a notebook, and I'm going to show you the steps you go through to produce that model. And then we'll move again to the deep learning stuff. So I'm going to create a new notebook, and I'm doing this deliberately a little bit slowly so that if you are following along, you can do so. I'm going to call this Predicting Breast Cancer. I want to write in Python. R works just as well, but what I want to point out here is that everything we're doing is running on Spark. So underneath the covers, we're writing Python, but it's executing as PySpark or Spark R. And if you're not familiar with Spark, it's incredibly important to the big data space. What Spark is an engine which is in memory, which is distributed, which is designed to do a variety of different topics. So you could have Spark do machine learning. You can do graph analytics with Spark. You can do SQL-like analytics. But today we're primarily going to be using Python to do machine learning models. So the first thing I'm going to do is pull in that data set that I just got. So I can do a header here. We can say, this is my notebook, and we're going to predict cancer. Then add a new cell, and we can get off to the races. So what's interesting about these is each of these can be individually executed. So I need to pull in my data. I'm going to go over here to the Data tab, And everything that you see in blue here, by the way, is sort of unique to the data science experience. So there's some nice things up here around data scheduling and collaboration, but what I want to do is insert my data set that I have in this project as a pandas data frame. Now, by the way, anybody that wants to get access to this project, just send me an email and I can add you as a collaborator. You'll be able to see all the code, all the data, and work with me on it as we move. Now, this code actually generates some code which is really slick, but at the same time it shows my password to me, not to everybody else. But since we're recording this, I'm going to take a moment to pause the screen, generate my code, and then I'll delete it. So I'm pausing the screen now. Give me one moment, please. I'm just making some adjustments to the code so that we get a good data set, and then again we'll be good to go. Okay, hold on. By the way, if you're interested in, again, following along, you can use, let's see, this beautiful notebook that I'm about to put on the screen over here while I'm generating my code. So I tell you what, let's actually walk through doing this the old-fashioned way, just so you can see it. So what I'm going to do is take my breast cancer data set that you saw me download earlier. I put it in here in my NIH video demo folder. And I'm going to drag and drop right onto my screen here. You'll see I've uploaded it. You'll see it appears down here. There we go. And I'm going to create that notebook again. So we're going to call this Predicting Answer. Create the notebook. And then do the code generation. There we go. I'm going to run it, and you can see I have my data. So again, I've got my identifier, my diagnosis, and then other data sets. So how do we move forward? Well, the first thing I'm going to do is rename this data file just to DF, something simple, because I don't like typing that every single time. So we're just going to re-execute this. All right. Now we move into the phase of what's called exploratory data analysis. Now, I like to use a tool called Pixie Dust to do this, which is a Python tool. And to make sure that we've got the proper libraries, I'm going to install Pixie Dust here. There we go. It looks like I'm good to go on that front. I'm going to tell my notebook that I want to use Pixie Dust now that I've got it installed. So I import. And now I can use the display call. So this is a function which actually generates something similar to what you might get with Excel or a tool that does charts and graphs. So I can say I want to do a bar chart, and I want to do it based on, I don't know, we could do the ID, and we can do the diagnosis here. And so I can do some exploratory data analysis in this way. I can look at distributions, things like that. Now, we talked about this earlier. I do have a slight imbalance between malignant and benign. So what I'm going to start to do now is leverage Python code to do a decision tree. So we've analyzed our data here. I'm going to show you that rows 200 through 210 look very similar, right? And then I'm going to have Python do some basic pre-processing for me. So if you haven't used Python for data science, this is one of the most important packages available, scikit-learn. So when I run this, I'm going to go ahead and do the install. Hopefully I've already got it installed. Yes, I do. Great. And now I'm going to do what's called pre-processing. So I'm calling that pre-processing function from scikit-learn, and I'm doing what's called a label encoder. And if you look up here, you can see my diagnosis is either malignant or benign. But to a computer, it's easier for systems to understand if it's a 1 or a 0. It's binary, it's on-off. So it makes our processing faster, and it makes it easier to use certain algorithms. So the first thing I'm going to do is check to see if any of my data is null, because that can cause problems. I might have to go back, impute data, that type of thing. Doesn't look like it. That's great. I'm lucky enough that this is a demo, and I can cheat a little bit. I've got a nice clean data set. The last thing I'm going to do is, if I'm going to change this data file, just as a best practice, I like to create a new one. So I'm going to say that my original data file is equal to this df2, just in case. Then I run code to do the transition that I talked about. So we change that diagnosis field to a 1 or a 0, and then we do a describe. So this gives us a statistical sample of what's going on in this data. What percentages are where. You can see here my diagnosis is either 1 or 0, but it might help me narrow down things like standard deviations and if that's relevant later on. I don't see anything that scares me here. So what I need to do now to create a valid model is segregate out some of that data. So there are multiple schools of thought on this, and we will test this later. But I'm going to bring in a thing here called train test split. And what this does is it takes all of my examples and it segregates out 20% of them in this case. You can see down there test size 0.2. That 20% is set aside, and it's not used in my building of my model. So when I teach the computer how to recognize breast cancer, 20% of it does not get taken into account, and that way I have a good way to test it later. So I'm going to run this code here, and you can see it executes. By the way, you know if it's executing, it's got a little star over there. So what we're going to do next is build a decision tree. And decision trees mimic human reasoning. They're very easy to understand, and I think they're not quite as powerful in some cases as some tools, like deep learning tools, but they're very quick and they're very easy. So I need this to generate some graphics here, and I'll just make sure that I have that installed. Great. And then I'm going to pull in the tree library. So the tree library in Python implements what's called a C45 decision tree. And you can see here that I'm saying don't use the column identifier, because the identifier obviously is not relevant to say breast cancer or not. And I've given it the splitting columns. So it's worth taking a moment to talk about decision trees a little bit more, and you'll see exactly what I mean in a second. As a human, we can reason, for example, how long is it going to take me to get to work today? Well, you've got variables that go into that, like is it raining, is it Monday, do you live in DC? All of those affect an outcome. Decision trees are a way for a computer, a machine, that's been given an outcome, like malignant or benign, to figure out which of the features that you've given it affect that outcome the most, and then work backwards. So we're going to do this processing here. I'm going to run this cell. It's executed. And now what I'm going to do is export this as a graph. So you'll be able to get a picture of the tree that it just generated. So you can see here, this is exactly the tree. There are many knobs to tweak when you do decision trees, and we're going to spend a little bit of time actually going over a lot of those. But what you can see is when your concave point mean is greater than or equal to 0.049, and the rest of these functions, we can then determine if something is benign or malignant. So when new data sets come in, when I get a new data set the system has never seen before, I can simply walk the tree, ask the question yes or no, and I can get a result. Really powerful stuff in terms of implementing things like business rules or being able to do multi-class associations and classifications. So this falls into the family of supervised learning because we're giving the computer an outcome and telling it to predict the outcome of a new thing. And like I said, decision trees are great because they're easy to understand, they're very fast, they don't need necessarily normal curves in data or things like that, but we can make it better. So for those of you who already know what a decision tree is and how to tweak those, this is where it gets more interesting, I think, for you. Let's interpret our tree. So we know what all these points mean, generally speaking, especially if you're a doctor, but we need to evaluate the model. Now remember, we left out 20% of our data. So what I'm going to do now is import that 20% and test it. I'm going to use the predict functionality here out of scikit-learn metrics to actually say, okay, so for those 20% that we didn't put in here, how good is this model? And you can see the output right here. So your accuracy is 92%. We guessed correct 92% of the time, or 93% if we're rounding up. AUC stands for area under the curve. Area under the curve has to do with a statistical method of judging the success of a model called receiver operating characteristic. But for those who don't know what ROC curves are, you can simply think of this as 93% of the time we manage to catch the malignant tumor. Now, if you're like me and you want to know if you have cancer, then 93% is pretty good, but it's not great. There's still 7% that we missed or misclassified. You could build something like a confusion matrix here to show false positives, true positives. That's easy to do. But instead, what I'd like to do is try to focus on improving this model. So this is our baseline here, 92, 93%, 94%. That's pretty good, but it has its limitations. So what I want to do is use something called gradient boosting. So I'm going to use this thing here called XGBoost, which is another Python package. And XGBoost has become very popular in things like Kaggle competitions because of how powerful it is in predicting outcomes. So we're going to use the XGB classifier instead of the traditional tree. So I import that. And don't worry about this deprecation warning, but our versions are back a little bit. So in order to improve this model, we're going to use a couple of different techniques. We're going to tune the parameters of the tree, things like gamma, lambda, tree depth, child weight, these types of things. And we're also going to use k-fold cross-validation, in this case 5. So to do that, I'm going to import cross-validation. Now, the way cross-validation works is it's a model used to measure how well a model generalizes when using the training set. And it divides it into even smaller training sets to gauge how the model performs on data it hasn't seen before. So for example, if we had 5 samples, we could call them A, B, C, D, E. We take a model built on A, B, C, and D, leave out E, and score it. Then I do the same thing for B, C, D, and E, and leave out A. I do this 5 times. And the reason I do this is because you could build a perfect tree if you used 100% of your data. But every time you get a new data set, you can't necessarily guess that correctly because you've over-fitted your tree. So just like a normal tree, sometimes these types of trees need paring back. They need to be told, don't be so specific. You need to be more general. That way I can go ahead and when I get new data in, I have a better model. So again, we're picking binary logistic here because we're trying to pick whether it's benign or malignant. You can leave these. We can get into a detailed discussion about some of these later if we need to, but I'm just going to set those right now. I'm going to do it 30 times. So I run this, and we're now good to go. So what I'm going to do next is bring in libraries to plot this out, which you'll see here. And then I'm going to build a function. And again, I'm not going to go into the specifics of the code here, but what's important here is that I've got a function to evaluate the model. It's going to iterate over the data, and it's going to try to increase our area under the curve and iterate and iterate and iterate until it can't get any better. So when I run this piece here, you'll see it running in the background, and we'll call the function. So again, don't use ID. Call the function evaluate model. Use the training data. The features are what we've just described, and execute. So you see here it's running again and again, and the area under the curve is going up and up and up significantly. So what we figured out here is that by using k-fold cross-validation, we're doing what's called boosting the tree. We're using multiple trees in an ensemble to get a better result. So now we're doing pretty well. We've got a list of which features are most important, right? These are the things that a doctor would look at first to determine if something is benign or not. And we've got a much better accuracy and area under the curve. But I think we can even do better. And this is where the art of data science comes in. I often joke with my wife that it should be called data art instead of data science. So we're going to do a couple of things here to do what's called tune the max depth and the child weight. So the max depth of the tree is how many nodes can I have. And again, you don't want a tree that's super complicated that overfits to a data set. So we want to figure out what our max depth should be. And we want to figure out if there is something like this texture mean, and clearly it's off the charts in terms of importance in predicting cancer, that its importance doesn't make the others less important. Because there may be fringe cases where the radius worst or the concave points mean is far more important than the texture mean. Fringe cases, these types of things. So this is where the tuning part comes in. So in order to do this, I'm going to go ahead and build another function here where here's our default model. But we use a thing called grid search CV. So it's cross-validating again. It's going to run, and it's going to find that the model that works best has a max depth of 5 and a minimum child weight of 2. Now, I made a mistake here, which is always good during a live demo. I forgot to import grid search CV. So I need to go ahead and make sure that I include from scikit-learn, move that up, run that, and now we shouldn't have a problem. You can see it's executing, and it will produce results in a moment. Now, another piece of the puzzle is something called gamma. So gamma makes the algorithm more conservative, which means it's less prone, again, to overfitting. You'll see here, by the way, that it went down up to 6 and then back down to 5 and then determined that child weight. So the way we're doing the scoring is that area under the curve still. So that's good. Now we have another variable which we can add to our study. To evaluate the gamma and the lambda, we're going to use this code here. So we're using our same evaluate model. We're including that max depth and child weight, which we just figured out from up here. And we're going to execute that to see, oh, excuse me, I forgot a piece of code here. Let's not forget to figure out what the gamma should be. Here we go. Here's how we figure out the gamma. So again, we're doing a test. And to do this, we're iterating over the data. Now, once you get to very large data sets, making sure that you're using a scalable technology underneath the covers like Spark is really important. Because as we evaluate models, we need to test different models, we need to test different parameters, and there are going to be fringe use cases where the computer may see something that we don't. So what we've determined here is the ideal gamma. You can see that there. We're going to set the gamma in our original classifier, and we're going to retest now, see how we're doing. I would argue that we're probably, hopefully, doing better. Yeah, so we're getting some really good results now. We're talking about 99, 98% accurate. Similar features, importance. That's to be expected. So there are more sampling parameters, and I've got a limited amount of time on the call, so I'm going to put the code here so you can go check it out later. If you have access to data science experience, you'll be able to see this easily in the sample models there. But I'll run this. You'll get an output. Here's lambda and alpha. Again, we're adding tuning parameters by using a very sort of regular scientific process where we execute, test, execute, test. And again, it takes a little bit of time to process, even when running in Spark. One of the nice things about data science experience is that this is all free. Everything you're seeing today is free, including the storage and the execution, but I can scale that up and down. So if I have a very large data set, instead of using 2 cores like I am on this, I can scale it to 300 cores or whatever I need. So that's kind of helpful. So we'll let these run. And then finally, we'll run our final model. Because now we have a good idea as to exactly what to use for alpha, gamma, the child weight, the depth, the number of estimators, and the learning rate. How do you think we're going to do? Pretty good? I hope so. So we'll run this. And here is going to be our final prediction. Bring in the data, use this, and spit out the answer. So I think what we'll have at the end of this is a model which effectively is 99.9999% accurate, which is pretty good. If I'm a doctor, I think that's a pretty good rate for me identifying stuff or not missing stuff, especially malignant cancers. So we're much better than we were. That's the original, right? 98%, and here's where we are right now, 0.99999. So pretty solid stuff there. To recap, what we did is we got our data set, which you see there. We made sure we had library. We did some basic exploratory data analysis. For the purposes of a demo, this is usually where you spend a lot more of your time, but we're not going to do that today. We did some basic statistical descriptions, and then we started down the path of the tree. So we created a basic tree. We validated that that approach works, which is great. And then we actually went and created a more advanced tree by taking advantage of an ensemble model, a boosted tree. We then used a code to actually regenerate all of the different parameters to that function. And then we iterated over that to increase the score for all of the different parameters that we think are worthwhile. So we started out with a pretty good result, and we're going to end up with a great result. Now, there are some of you who are thinking, I don't know Python. I don't ever want to do this. Well, we can do it automatically too. I'll take just 30 seconds to do this, but you can see here I've got the same data sets. If I go over here to analytic assets and try to tell the system to create a new model, I can do that as well. So we'll just call this new model. And you can find this type of technology in a lot of modern examples of tooling like SPSS Modeler or SAS or those types of things. But effectively what we're doing here is what I call auto modeling. So I take in a data set, it figures out the hyperparameter optimization, model selection, and then it gives me whichever one scores the best. So this would be for somebody who doesn't ever want to touch a keyboard, doesn't want to go near Python. You still have the option to be able to do predictive analytics. So in this case, select the column that you want to predict, diagnosis. I want to use all the columns. It's a binary classification. And I want to do 4 different models here that we can train. So in the background, the system here is doing everything that I just did manually, and it's going to do it presumably pretty quickly. But there are options. I view this as you could give something like this to a doctor. They could evaluate if any of the models work, and then there's a handoff to a seasoned data scientist who's going to go ahead and run that code that you just saw. So what it's doing in the background here is it's going to actually train and evaluate all these different models, do the same types of things that we just did in Spark, and actually spit out performance. And you'll actually see which ones work best. We use the decision tree classifier, and here it's only getting it to about 92% for the AOC. We were able to do better as human beings, and I think that makes us feel pretty good about ourselves. And so last but not least, we'll let it do its gradient boosted tree. And it turns out here that random forest might actually be a really good way to go. So random forest is a great technology for decision trees, where you're building sort of multiple decision trees on each other. So we do have a model now where we can actually deploy this and send data to it. Anyway, so we've talked now about predicting breast cancer, and we've done it using highly structured data. And I mentioned before, some might say that that's cheating. How do we do this against unstructured data? Well, there's a quote out there which I like a lot, which is, in machine learning, having more data is almost more important than having better algorithms. So I don't have images of breast cancer lying around. I could probably go find some, but what we're going to do here, just to show the basics, is show how a different variety of machine learning, something called deep learning, can be trained to recognize handwritten digits. This is a classic example, but if you haven't seen it before, it can be very effective. One thing to note here is that deep learning is significantly more computationally intensive, usually, than traditional machine learning. So I'm not going to run this one interactively, but you can see the results from a previous run. So what is deep learning compared to the machine learning and the tree-based learning that we just talked about? Well, deep learning tries to simulate how a human brain works. And it has, the original ones were called neural networks, just like we have neurons. So it tries to make its own connections, and then it builds what's called hidden layers. So a deep learning model can have hundreds of layers, and it will assume or try to think about a problem the same way a human thinks about a problem, by connecting ideas, testing it out, seeing what works. If it doesn't work, it goes on and creates a new hidden model. Now, that's a very rudimentary explanation of deep learning. I'm happy to go into some of the math after this, or maybe during a different session, but that's sort of what you need to know for now. And an important part about deep learning is that we figured out that things like graphics processing units, GPUs, the same thing that runs video games, is actually really good at doing matrix math. And deep learning tends to involve a lot of matrix math. So at IBM, we are talking about big data here. When you need to do deep learning against large amounts of data or large streams of data, you have to use GPUs. So that's why cars that are coming out now that are learning to do image detection and find other cars and people on the road are using GPUs on board. So enough about deep learning for the moment. Let's take a look at what we're going to do here. So I've got data that I borrowed from Google of handwritten digits. So there's a large database of these handwritten digits. And it's easy for a human to understand what makes a 7 a 7, but it's actually very difficult for a computer to read a picture and understand what's in it. This is admittedly a simplistic example, because you could have a different example might be, show me pictures of birds, or show me pictures of cancer on a lung x-ray. But with that, you're going to have multiple different angles. You're going to have different locations for the cancer. So it's not as simple, it's not as black and white. And we'll talk a little bit about that more later. Anyway, what I'm going to do here is install a package called NoLearn. And NoLearn is a Python package that does deep learning. In fact, we're going to be using something called a deep belief network. And deep belief networks are pretty quick to execute against simplistic data sets like this one. So we're using it here, but we can talk about other algorithms as well. So as I step through this, I've got my scikit-learn, which is the same thing I had from my previous example, where I need to separate out test and training. You'll find that's a common theme throughout all of data science. I've got metrics, right? So how does it do? Data sets, right? So sample data sets. This is the deep belief network, DBN, and then some Python math and other image stuff. We're going to pull in data from Tensorflow, and this is where we're pulling our images and our labels. So for every image of a handwritten number 9 is a label that tells the computer that this is a 9. It's worth mentioning TensorFlow because there are a lot of libraries out there put out by different companies and different open source groups. Things like Keras, TensorFlow, Caffe, Torch. These are all names that are really powerful engines that are helping people sort of do things like machine vision and that kind of thing. But it's a little bit difficult at the moment to work with all of them at once because there's no real standard for that. It's sort of the Wild West. So that's something that IBM is spending a lot of time on, is making sure that if people want to use these things, they all work together and they all work together in a similar fashion. So in the data science experience here, we have technologies like TensorFlow built right in. So you can use them and you can execute on GPUs and things like that. So right here, I'm separating out my training and test, just as we did before. As you can see here, I'm leaving out 33%, not 20%. So I've got a database of about 37,000 or so images used for training, and then another 36,000 or so for testing. So that's pretty good. All right, so now we need to train the pattern recognition model. If you want to get into the very sophisticated math that goes into some of this stuff, I can highly recommend you go to this link. There's a bunch of data there on how we do this. But effectively what we're doing here is we're telling the deep belief network solver, which is this DBN call here, that it can go 300 layers deep, because we figured out that we think that that's around the most optimal for each of the 10 digits. And that's that 10 epochs here. So this part takes a while if you run it on your own, especially if you don't have GPUs to accelerate it. So each of these represents the 300 layers for each digit. So it goes through all 10 digits. And if you were at the point where you were trying to do something extremely difficult to recognize, like very small cancers in X-rays that require sophisticated technicians to read, this is where you would probably stray away from a deep belief network and move towards something like a convolutional neural network. And convolutional networks are better able to take into account the entire picture and better able to layer different angles, different versions of what the thing's looking for, because a cancerous tumor looks completely different from the side than it might from the front. My wife is spending a lot of time on this actually right now, doing some work for the Transportation Security Administration, where they're trying to automate the process of detecting people walking through X-ray machines and hiding metal or other weapons in their clothes or in their bodies. So really application across the board on this one. Some good stuff there. And what's interesting about this now is my report. So I call dbn.predict against the training data. And you can see here my precision and recall is great. So I've built a model where I've been able to actually teach a computer to read handwritten digits. And I've done it, I don't know if you've seen, but it's maybe less than 100 lines of code, because I'm able to take advantage of some of these really sophisticated packages in Python and R. One of the interesting things, just as an aside, about this space right now is that all of the really interesting stuff is happening in the open source. This, I think, analytics is the shining example of how open source can be the most effective way to get data out there, get code out there, and increase innovation. So IBM a while back, even though we have our own technologies like SPSS, we're not abandoning it, but we're certainly embracing how the accelerated process of open source is really changing the world. So we're very excited about that, and that's one of the reasons we built this data science experience, to make that process easier. So I'm going to define a function here where I call it random image. So it picks it out. It picks a random image out of my entire data set and tries to figure out what it is. And let's see how we do here. So I know I ran this before, and it occasionally does miss things, but actual digit is 7, predicted is 7. Pretty good. Oh, we think it's a 5. It's definitely a 5. Here's a tricky one. What's that? 7? It's a 7. So we're 100% in this case. Not bad, especially when they get a little wonky like that. I did not write this notebook. Of course, the people who do write it are all listed here. So some of them are colleagues in academia, industry. Some of them are us. But here's an example, again, a very simple example of how we can use deep learning to do image classification. So we have Watson for Oncology. I'm sure some of you have heard of this. We've spent years working with things like convolutional neural networks, with Watson's natural language processing and all that, to get Watson, the supercomputer, to be able to use this type of thing in the background and actually recognize cancer and then tell you what to do about it. What are the best forms of treatment? Those types of things. Now, we're making pretty good time here. I think I've got a couple of minutes left, so I'll highlight some other technologies that I think are really fascinating, and then I'll leave 10 minutes at the end for questions. So one of the other most important things that I think we have to really focus on is genomics. I don't know if any of you are in the genomics field, but one of my favorite packages is something called ADAM. So if you go out there and you look up Apache ADAM, A-D-A-M, you'll see that there is actually an open source distribution that runs in Spark, meaning highly scalable, that's able to do certain genomics tasks. Now, I am by no means a geneticist here, but what I'll show you here is something called counting K-MERs, K-M-E-Rs, something that previously took, I don't know, a year to do. We can now do divide and conquer, spread across multiple PCs or cloud systems, and produce tangible results. So here, if I say a 10, where K is 10, it's looking for strings of 10, it's counting them, and this is actually doing it out of a mouse's genome. So this is something that's obviously not as pretty as some of the other stuff you've seen, but it's things we're working on at IBM. How do we work with the FDA to look at the genetics of certain trends or chemical formulas, break them down, and do drug safety type stuff. So fascinating stuff there. Again, that technology, if I can give them a plug, is called ADAM, A-D-A-M. And if you're a geneticist, I highly recommend you look into it. Good stuff there. And the last piece that I'll bring up is something which may seem trivial, but it's actually super important. We all work in environments where we have constrained resources. And so the other side of predictive analytics is something called prescriptive analytics. If I can predict, that I'm going to need a certain amount of a drug or anything like that, then I need to know what to do about it next. So this is something that's a classic computer science problem called the nurse assignment problem. And here we're combining Python with IBM's resource optimization engine. So I need to schedule all these nurses together. I load in their data, and they each have specialties. They each have vacation times. They each have costs associated with them. Some of them are in different locations. Some of them don't like each other and won't work with each other. That's exactly what a prescriptive analytics engine does, is you give it data about what you're trying to accomplish, and then you give it resource constraints. And we find the most optimal way to do that scheduling, or to have the right drugs at the right hospital at the right time based on needs, these types of things. So a really important part of predictive analytics, something which can be absolutely integrated in with the open source technologies like Python and R, and then built out so that you can actually do these prescriptions or prescriptive analytics on the fly. So putting the right vehicles in the right place. This is something that I personally spend a lot of time with logistics, right? Groups like the Army, Navy, that kind of stuff. So all that being said, I'm now at 12:50. I'd like to invite my host to jump back on. Hopefully he's not passed out.
No, sir, Jonathan, I'm not. Thank you so much for that really great tour through the IBM data science experience. That was fascinating. We have a question where one of our listeners was asking about how the code defines the feature importance score in your decision tree.
Yeah, great question. So let me go back to it for you here. When you do things like decision trees, you get feature importance because it does really one of two things. So this is something you can go and look up later, but it either uses what's called a Gini index or an entropy score. And what it does is it determines what the most important part of that data set is, because it's able to split the data based on it. So let me just bring up my model here. So part of that library is what we were talking about, and I'll get down to the exact spot. But what it's realized here is that this concave points mean, if it's greater than or equal to this, you're almost always in a certain category. Another easy analog might be gender, right? If you're trying to determine if somebody's a male or a female, you could use data like how much do they weigh, how tall are they, but I think if you just looked at their physiology, that gives you hands down the biggest clue, right? Maybe not all the time, but so an example of feature importance there would be we're at the root node of the tree, and it's figured out that pretty much anything to the left or right is going to have a huge impact on whether, in this case, it's benign or cancerous. So let's see. The actual code part that gives you that output is right here. So we're doing this part of the algorithm. We're getting the score, the feature score, and then sorting it by how high that score is. So 10, obviously, and then descending. Hopefully that answers the question. I will put up my contact information so you can ping me if I didn't list it there. But any other questions?
Yes, we do have a couple other questions. So someone is asking, do you have any resources on choosing the right machine learning model for your particular question?
Yeah, and this is where it gets to that data art piece as well. So we have technologies that do automatic modeling. I showed you one of them today. We call that IBM machine learning. And what that does is it separates out the obvious, technologies, obvious algorithms or models for a problem, because some just aren't appropriate for certain things. And then it will go through and do subtle testing. We call it cognitive assistance for data science. So there are other technology platforms out there that do that. If you want to do it the old-fashioned way, unfortunately, it's sort of an understanding of the models, and this is where the art comes in. So you may understand that random forest works really great for certain problems, but you've got more ability to tweak algorithms or things there. So a lot of it's going to be personal experience, unfortunately, but we do have technologies like Watson Analytics and Watson Machine Learning that will go through, test a bunch of models, and then give you what it thinks is the strongest solution. So that's technology that's been out for a while. But again, a lot of it can be just based on personal experience, unfortunately.
Right. Do you see a lot of people interested in these sorts of solutions who are working in the area of clinical trials or in drug discovery, for example?
Absolutely. So we do a ton with clinical trials, clinical informatics. The drug discovery stuff I'm not as strong on, but we do it there. When you think about it, the platform is a highly scalable, inexpensive platform. where you can have it run either up in the cloud or on your own site. And that alone is kind of nice, because I can take a data set and I don't have to pay $1 million to run it through a supercomputer. And you have a huge amount of flexibility and control by using this open source stuff, because there are algorithms that come out for clinical informatics out of certain research institutions monthly, right? Where I can go download the latest and greatest based on some paper I just read. So we're doing some of this at the VA right now. I know there are teams at the NIH working in sort of small teams. One of the problems with the industry right now is it's just a little immature. It's a lot like sort of business intelligence was back in the 90s, where everybody had their own Excel spreadsheets on their desktops. So we're trying to help with that, right? Get around some of the governance problems, bring people together with repeatable data sets, and be able to share the insights that they're coming up with.
Yeah, well, that's fantastic. And one of the things that you had mentioned in a couple of times, sort of in passing, is everybody's kind of a little familiar with the Watson supercomputing system, and I'm curious if this has exactly how this dovetails with that, or perhaps it doesn't at all. But I thought maybe if you could explain if there was, that would be very interesting.
Yeah, great question. So there's some core logic that Watson does that helps us do things like understanding language and intent and beliefs. So what you saw today is what we call our Watson data platform. Not that unstructured data isn't data, but it focuses much more on structured data and certainly on the open source. So we do use Watson within the Watson data platform, but it's fundamentally different than the Watson that you see on TV that plays Jeopardy and things like that.
Right.
That Watson is less about predicting the future using math and more about interacting with humans and understanding written word. So when you bring them together, you get these nice interfaces where I can bring in a structured data set and I can ask a question in regular old English, and Watson will understand that, translate it into a mathematical equation, and then we'll use some of these mathematical techniques and open source analytics on the back end to output the correct answer. So it's an exciting time to be at IBM.
It's interesting, and of course, I could load my own data if I wanted to. If it were, you know, I do work in neuroimaging, for example, and if I had not necessarily the raw images, but I had measurements made on those images, I presume I could load this in as my own data source and then carry on, right?
Absolutely. So everything you saw today is available up at datascience.ibm.com. Doesn't cost anything. There's tons of tutorials, sample notebooks, sample data sets to use. You can load up your own stuff. And the other thing I'll put in there is we have a website. It used to be called Big Data University, so I think you get a sense as to what it is. But we've now called it cognitiveclass.ai, and that's all free training on the big data space. So if that's of interest to you, I say go check it out. And we always appreciate feedback on that too.
That's fantastic. Let's see, what time do we have here? We only have like a couple of minutes left, but I don't see any other questions flying in. But anyway, maybe I'll take this time to once again thank Jonathan Entwistle from IBM to give us a rundown of the data science experience. It looks like very useful, very well thought out, very flexible and scalable solution for dealing with a lot of our biomedical data types, and being able to document and share that with others and other colleagues. So it sounds very exciting. I hope that those of you who are interested will reach out to Jonathan with any additional questions via his contact information. Check things out at datascience.ibm.com or cognitiveclass.ai and learn more about it. Once again, this is our Fundamentals of Data Science seminar series, and do watch in your emails for announcements about our further sessions and our further speakers and information about them. And once again, let me thank Jonathan for his lecture this morning, and thank you for joining us. Thank you very much, everyone. Have a wonderful day.
Thank you much.